Properties of matrix addition. Hello, everyone. Let's begin our lesson on the properties of matrix addition. To start, let's quickly recap. In our previous section, we learned the basic mechanism of adding two matrices, which involves simply adding their corresponding elements together. However, performing the calculation is only the first step. To use matrices effectively in more advanced studies, such as higher mathematics and physics, it is essential that we understand the algebraic laws that govern these operations. These laws provide the theoretical foundation that allows us to manipulate matrices with confidence. The good news is that matrix addition is quite intuitive, as it behaves very similarly to the addition of real numbers that you are already familiar with. Over the next few slides, we will explore the four fundamental properties of matrix addition in detail. We will examine each law, walk through step-by-step examples, and discuss how to apply them correctly. Let's get started. 1. Commutative law. Now that we have established the basics of how to add matrices, let us move on to the first of the four fundamental properties, the commutative law. The commutative law simply states that when you are adding two matrices, the order in which you add them does not change the final result. In mathematical terms, if we have two matrices, matrix A and matrix B, and they both have the same dimensions or order, then matrix A plus matrix B will always equal matrix B plus matrix A. To help you visualize this, let us use a real-world analogy. Imagine you are managing two different branches of a store, branch A and branch B. If you create a matrix to represent the sales of items at branch A and another matrix for branch B, the total sales will be the same whether you add the sales of branch A to branch B or branch B to branch A. The total remains unchanged regardless of the sequence. Let us look at a step-by-step example to prove this. Suppose we have matrix A, which is a 2x2 matrix with 2 and 5 in the first row and 1 and 3 in the second row. And we have matrix B, a 2x2 matrix with 4 and 1 in the first row and 0 and 6 in the second row. First, let us calculate matrix A plus matrix B. We add the corresponding elements. 2 plus 4 gives us 6, 5 plus 1 gives us 6, 1 plus 0 gives us 1, and 3 plus 6 gives us 9. This results in a final matrix with 6 and 6 in the top row and 1 and 9 in the bottom row. Now let us reverse the order and calculate matrix B plus matrix A again. We add the corresponding elements. 4 plus 2 is 6, 1 plus 5 is 6, 0 plus 1 is 1, and 6 plus 3 is 9. As you can see, we have arrived at the exact same resulting matrix, 6 and 6 in the top row and 1 and 9 in the bottom row. Therefore, we can conclude that since both results are identical, matrix A plus matrix B is indeed equal to matrix B plus matrix A. This property is very helpful, but it only applies to addition. In our next slide, we will see how this concept extends when we deal with three or more matrices through the associative law. 2. Associative law. The associative law states that when we are adding three or more matrices, the way in which we group them using parentheses does not change the final resulting sum. In formal terms, if we have three matrices of the same order, which we will call A, B, and C, then the sum of A and B added to C is equal to A added to the sum of B and C. To make this clear, let us walk through a step-by-step example. Suppose we have three matrices. Matrix A contains 1 and 0 in the first row and 2 and 1 in the second row. Matrix B contains 3 and 1 in the first row and 0 and 2 in the second row. Finally, matrix C contains 1 and 2 in the first row and 1 and 0 in the second row. First, let us calculate the left side of our equation, the sum of A and B, then added to C. We begin by finding the sum of A and B by adding their corresponding elements. We get a matrix with 4 and 1 in the first row and 2 and 3 in the second row. Now we take this result and add matrix C to it. Adding 4 plus 1, 1 plus 2, 2 plus 1, and 3 plus 0, we arrive at a final matrix with 5 and 3 in the first row and 3 and 3 in the second row. Now, let us see if we get the same result by changing the grouping. We will calculate a added to the sum of B and C. First, we find the sum of B and C adding their corresponding elements gives us a matrix with 4 and 3 in the first row, and 1 and 2 in the second row. Next, we add matrix A to this result. Adding 1 plus 4, 0 plus 3, 2 plus 1, and 1 plus 2, we get a final matrix with 5 and 3 in the first row, and 3 and 3 in the second row. As you can see, the results from both methods are identical. This confirms that the associative law holds true for matrix addition. Now that we have established that the order of two matrices does not affect the sum, let us move on to the second fundamental property, the associative law. Having seen how we can reorder and regroup matrices, we will now move to the next slide to discuss the existence of the additive identity, where we introduce the concept of the zero matrix. 3. Existence of additive identity. To understand this, think back to basic arithmetic with real numbers. We know that 0 is the additive identity because adding 0 to any number, for instance, x plus 0, simply results in X matrix algebra follows a very similar logic. In this context, we have what is known as the zero matrix, denoted by a capital O, which is a matrix where every single element is 0. Formally, if we have a matrix A of any given order, such as M by N, and we add it to a zero matrix O of that same order, the result is always the original matrix A. In other words, A plus O equals A, and likewise, O plus A equals A. Let us look at a step-by-step example to illustrate this. Suppose we have a 2 by 2 matrix A consisting of 7 and -2 in the first row and 4 and 8 in the second row. We will pair this with a 2 by 2 0 matrix O, where all the entries are 0. To perform the addition, we add the corresponding elements from each matrix. 7 plus 0 is 7, -2 plus 0 is -2, 4 plus 0 is 4, and 8 plus 0 is 8. As you can see, the resulting matrix is exactly the same as our original matrix. This confirms that the zero matrix acts as the identity element for matrix addition. Now that we have discussed the commutative and associative laws, let us move on to the third fundamental property, the existence of the additive identity. Understanding this identity is essential, as it leads us directly into our final property, the additive inverse, which we will explore in the next slide. 4. Existence of additive inverse. Just as every real number has an opposite that brings it back to 0, for every matrix A, there exists a corresponding matrix called -A, which is known as the additive inverse. The defining characteristic of the additive inverse is that when it is added to the original matrix, the resulting sum is the zero matrix. To obtain this additive inverse, you simply change the sign of every single element within matrix A. This means positive values become negative, and negative values become positive. In formal terms, if we have a matrix A, then matrix A plus -A, or negative A plus matrix A, will always equal the zero matrix, O. Let us walk through a step-by-step example to illustrate this. Suppose we have matrix A, which contains 3 and -5 in the first row, and 2 and 0 in the second row. In the first step, we find the additive inverse, -A. By flipping the signs of all elements, we get -3 and +5 in the first row, and -2 and 0 in the second row. In the second step, we add matrix A to its inverse, -A. We add the corresponding elements. 3 plus -3 equals 0, -5 plus 5 equals 0, 2 plus -2 equals 0, and 0 plus 0 equals 0. As you can see, the result is a matrix where every element is 0, which is our zero matrix, O. Now that we have discussed the zero matrix as the additive identity, let us move on to the fourth and final property, the existence of the additive inverse. Having explored all 4 properties, we will now move to the next slide to summarize these key takeaways and discuss some common pitfalls to avoid. Key takeaways. Now that we have walked through each property with detailed examples, let us summarize the key takeaways to ensure you have a solid grasp of these concepts before we move on to common pitfalls. First, let's recap commutativity. As we demonstrated, the order of addition does not matter. Therefore, matrix A plus matrix B is equal to matrix B plus matrix A. Next, we have associativity. This tells us that when adding three matrices, the grouping does not change the result. In other words, the quantity matrix A plus matrix B, all added to matrix C, is exactly the same as matrix A added to the quantity matrix B plus matrix C. Third, let's remember the additive identity. The zero matrix, denoted by a capital O, acts as the identity element. This means that adding the zero matrix to any matrix A leaves matrix A completely unchanged. Fourth, we have the additive inverse. For every matrix A, there is an opposite matrix, which we call negative A. When you add matrix A and matrix negative A together, the result is always the zero matrix. Finally, and most importantly, please keep in mind the fundamental requirement. All these properties hold only if the matrices involved have the same order. If the dimensions do not match, these operations simply cannot be performed. Keep this specific point in mind, as we will discuss some common mistakes related to this in the next slide. Common mistakes. First, let's talk about ignoring the order. It is a frequent mistake to try and apply the commutative or associative laws to matrices of different dimensions. Please remember that matrix addition is strictly undefined if the orders of the matrices are not identical. You cannot add a 2x2 matrix to a 3x3 matrix, regardless of the properties we've discussed. Second, be very careful not to confuse the different types of identity matrices. In our previous slide, we explored the zero matrix, denoted by a capital O, which serves as the additive identity. Do not confuse this with the identity matrix, denoted by a capital I, which is the multiplicative identity. To keep them straight, remember that the zero matrix consists entirely of zeros, whereas the identity matrix has ones along the main diagonal and zeros everywhere else. Finally, watch out for sign errors. When you are calculating the additive inverse, which we represent as negative A, ensure that the sign of every single element in the matrix is flipped. A common slip is to miss an element or forget to change a negative to a positive. Also, keep in mind that while you apply the sign flip to all elements, negative 0 simply remains 0. Now that we have covered the fundamental properties and the key takeaways, let's conclude by discussing some common mistakes students often make. Paying attention to these will help you avoid simple errors in your exams.